Welcome back! Now that we've finished the installation, let's jump into some code. First and foremost, we'll open up a new Jupyter notebook. Inside of your terminal, we will navigate to Desktop, CD Desktop, and we will open up a new Jupyter Lab instance. Alright, we'll start a Python 3 notebook, which we will rename as perceptron.ipynb. You can go ahead and call it whatever you want. Just like before, first we need to plot our training data just like we did in the last section. Since I've already explained this, we're not going to reinvent the wheel. So first we will just import numpy as np, and we'll also import matplotlib.pyplot as plt. Pretty standard stuff so far. We'll just run this cell, and what I actually did is prior to this lesson, I've left you an article with a piece of code that I want you to use inside of your project. So make sure to do just that. Copy and paste it and run your code. Again, we've already covered this. If you're not sure what this code does, make sure to revisit in lesson number 7 of the last section. But essentially, we're just declaring 500 points in the top region, 500 points in the bottom region, such that they're normally distributed with a standard deviation of 2. We're then stacking these points in an array and plotting them onto matplotlib. And right here is just the array of labels, which corresponds to all points in the top region having a label of 0, all points in the bottom region having a label of 1. And lastly, we want repeatable results every time we run our data, which is indeed what we have thanks to np.random.seed, which simply seeds our number generator. That way, if we ever have an error in our model, we can reproduce the error every time. Now again, all of this stuff should be very familiar to you. If not, make sure to revisit the last section. And before we get started, to render the figures in our notebook as static PNGs, we will write the command %matplotlib inline. Nothing major. Anyways, to get started with the good stuff, what we'll do first is we will import the Keras library. And from the Keras.model subpackage, we'll need to import the sequential class. A sequential model, as per the official documentation, is a linear stack of layers. Neural networks are actually organized in layers containing interconnected nodes. In the most basic case of a neural network that we previously discussed, the perceptron, the first layer was actually the input layer, which was processed via a linear system of weights and biases, and the output layer resulted in a predicted output via the activation function node. So in this perceptron, we have two layers, the input layer and the output layer, nothing else. So what we'll do is inside of a new cell, we will set a variable model equal to an instance of sequential. Having defined the sequential model, let's first run the cell. Alright, having defined the sequential model, we can now start adding layers to the structure. As mentioned earlier, we are going to create a perceptron with an input layer containing 2 nodes and an output layer with a single node. Using the model.add function, we can now begin to add layers to our neural network. What we'll do first actually is from the Keras.layer subpackage, we'll need to import the dense class. In a dense layer, every node in the layer is connected to every node in the preceding layer. So inside the argument, we will specify the properties of the dense layer. The first argument is the units, which will simply equal 1. We'll have a single output for our perceptron, and since this is the first layer being created, we must also define a number of input nodes. This is done through the second argument, input shape, which we will set equal to 2. Since recall in the old code, we only had 2 input nodes, x1 and x2. Perfect. The final argument, the activation, defines the activation function used in the output layer nodes of the perceptron. Really all we've talked about so far is the sigmoid function, and that's what we used in our old code. So we'll just go ahead and write that. And if you were to actually compare this to how we implemented sigmoid in pure Python code, this is clearly much more concise. Instead of specifying the math yourself, all you have to do is write the tag sigmoid. Alright, having specified the layers of our network, to compile a Keras model, we need to make use of an optimizer. So what we'll do is from the keras.optimizers subpackage, we will import Atom. The Atom optimizer is one of many optimization algorithms. What's distinctive about the Atom optimizer is its adaptive learning method algorithms. To truly understand the importance of the Atom optimizer, let's talk about the vanilla gradient descent algorithm that we implemented in the last section with the following formula. By taking the current parameters and subtracting the partial derivative of the error function with respect to its parameters, we're iteratively taking a step in the direction of the negative of the gradients, in the direction of the least error, and therefore updating the weights and the bias in the direction with the least error. The problem with taking this derivative is it's too expensive, since we're essentially just multiplying a scalar times the coordinates of all the points. What if we're dealing with 1,000,000 points or 100,000,000 points, which represents the population of some country? The fact that we're looking at all the training examples at the same time is why we refer to this form of gradient descent as batch gradient descent. In order to compute this derivative term, we have to read into our computer's memory all 100,000,000 records, then taking the derivative and multiplying the learning rate, and we're doing all of that just to take a single step in the direction that minimizes the error. Then to take another step, we have to repeat this entire process, which would be very computationally intensive, and would take a very long time for the algorithm to converge to an absolute minimum. A more efficient algorithm that better scales to large data sets is stochastic gradient descent, which would be much more computationally efficient than the vanilla gradient descent. Why? Well, as we just saw, batch gradient descent computes the gradient using the entire dataset, whereas stochastic gradient descent computes it through a single sample. If you're interested about the specifics of stochastic gradient descent and how it works, feel free to ask me in the Q&A or just send me an email, we can discuss it further. But for the sake of moving on to the code, the Atom optimization algorithm is a combination of two other extensions of stochastic gradient descent, notably AdaGrad and RMSProp, and is a very efficient stochastic optimization method in updating the weights of our network. What distinguishes it is that in stochastic gradient descent, or even the vanilla gradient descent algorithm that we implemented in the last section, is we had to be careful to choose a proper learning rate. A learning rate that is too small leads to very slow convergence towards the minimum, while a learning rate that is too large can hinder the convergence. Where these variants maintain a single learning rate for all weight updates, such that the learning rate does not change during training, the Atom optimization algorithm ultimately it computes adaptive learning rates for each parameter, and has been empirically shown to be a very popular algorithm in efficiently achieving good results when dealing with large models and datasets. In practice, Atom is actually currently recommended as the default algorithm to be used, so we'll go ahead and use it ourselves. So what we'll do is we will set Atom is equal to an instance of Atom, which will minimize the error with a learning rate, LR, is equal to 0.1. Now, before training our model to classify this data, we need to configure the learning process, which is done via the compile method, model.compile. Inside of compile, we need to specify what kind of optimizer we're going to use, what kind of error function, hint hint, cross entropy, and the metrics, which is a function that's used to judge the performance of our model. So the optimizer we'll use is Atom. Our loss function will equal some form of cross entropy, which, as you know, is the loss function that will help determine the error. Now, since we're only dealing with two classes, we'd expect a binary outcome of zeros and ones. And thus, we will be using binary cross entropy. Binary cross entropy. This calculates the cross entropy value for binary classification problems. If we were dealing with 3 or more classes, you would then use categorical cross entropy, which calculates the cross entropy value for multi-class classification. As for the metrics, a metric is very similar to a loss function. However, unlike the error function, whose results, as we saw, are constantly backpropagated to minimize the error of our model, the results from evaluating a metric are not used to train the model, but simply to judge the performance at every epoch, which is going to equal a list of functions. In our case, we're interested in the accuracy, which calculates the accuracy of how often the model's predictions match the labels of our data. Now, to actually train a model to fit our data, we'll use the model.fit function. This is the function that we use to start training our perceptron. To start training a model that perfectly classifies our data, we will first pass in the training data that we're going to use to train our model. X is equal to X, that's the keyword argument you have to specify, and then we will pass in the labels that we assigned to each data points. Y is equal to Y, such that labels of 0 will correspond to the top region and labels of 1 will correspond to the bottom region. Alright. And this makes sense, since by passing in the corresponding labels that we assign to each data point, that way it can distinguish as to which point should belong to which class. If, according to the labels, our points are misclassified, the error function will be high, and thus, through an optimization algorithm, we will act to minimize that error, so really important that we pass in the labels. So now we have our training data defined by their labels, and we'll be training our model to fit all of this data. Since all the data is labeled, that way the model can distinguish which points would belong to which class, and then we'll set the verbosity, verbose, is equal to 1. What that will do is simply display a progress bar of information relating to the performance of our model at each epoch. If you set verbosity equal to 0, it simply wouldn't print anything and we wouldn't know what's going on. And now an epoch, you might have noticed me talk about it a lot but never actually explain it. An epoch simply refers to whenever it iterates over the entire data set of points and labels to try and separate our data in discrete classes based on their assigned labels. So every time it iterates over the entire data set of points, that is an epoch. However, one epoch is too big to feed to the computer all at once, so we need to divide it into several smaller batches. More specifically, it will be a batch size of 50. You want to make sure your batch size is sufficiently big, that way it doesn't take forever to run your code, but you don't want it to be too big, since you don't want to feed it to your computer all at once. And since we have 1000 data points, 500 here and 500 there, with a batch size of 50, it will take 20 iterations to complete one epoch. And at each iteration, it's going to update the weights of the neural network, minimizing its error. That way it better fits the data given. And ultimately, the batch size really depends on the size of your data, and according to your GPU, how long it takes to process your data. A batch size of 50 is a pretty good number relative to the amount of data points that we have. Alright, now how many epochs should our line go through? Let's recall the concept of gradient descent, which updates the weights and biases of our network in the direction that decreases the error function the most. It's an iterative process, which is why we need to pass the full dataset through our neural network multiple times to ensure an optimized result. In other words, we need more than one epoch. If you simply specify one epoch, epochs is equal to 1, that leads to the underfitting, which doesn't capture the underlying trend of data. As the number of epochs increase, the more times it's able to update the weights of our neural network, minimizing the error and thus producing the optimal results. At the same time, you don't want to pass in too many epochs, since that can lead to overfitting, which is a modeling error that occurs when a function is too closely fit to a limited set of data points. This overfitting, we're going to see a lot of examples of it once we deal with deeper neural networks. And now, since we're dealing with a linear classification of relatively small complexity, as opposed to a deeper neural network with a higher complexity, which we will make use of later on in the course, one might think that overfitting isn't much of an issue, although a linear classifier can absolutely be overfit if used without proper care. However, if you have the right number of epochs, it's going to model your data just fine. Unfortunately, there isn't really a right answer as to how many epochs you should have. It really just depends on your data set. So what we'll do is we'll just specify epochs is equal to 500. It'll go through all of our data 500 times. Now 500 epochs is a bit much, I'll admit. Realistically, we're not going to need more than 10 epochs or so, but for the sake of demonstrating the training process and seeing a descriptive plot, we'll extend the training process to go with 500 epochs. Now don't actually get used to specifying too many epochs. You'll see that this can get pretty bad once I demonstrate this in the convolutional neural network section, as the model can start to overfit our training data and isn't able to generalize itself to new data. But regardless, we'll cross that bridge when we get there. Now finally, we're gonna set shuffle is equal to true. This one should be new to you. So as to shuffle our training data before each epoch. As we use gradient descent to update the weights in the direction that decreases the error the most, as it keeps minimizing the error, it'll tend to get stuck in a local minimum of some sort, rather than the absolute minimum. And our goal is to minimize the error the most, so what you want to do is ensure the absolute minimum of your loss function, to decrease the error as much as possible, thereby maximizing the accuracy of our model. And so if you are dealing with static training data that's unchanged over all training iterations, gradient descent algorithms will tend to get stuck in these local minima, and the solution to this is to simply shuffle your training data. So what that does is it shuffles the rows in your data, and for each given iteration, trains only a subset of them. This ensures that the subset of training data changes with every single iteration. And thus, if our algorithm were to get stuck, it would simply help it kind of bounce off the local minimum. Alright, we are finally ready to run our code. And you know what, before doing so, and I'm noticing an error, this should be a lowercase y. We don't have any variable that's a capital Y. And aside from that, we should be good to go to run our code. It says the name dense is not defined. Maybe we need to run our first cell. Let's try that. Alternatively, you could have just pressed run all, but we'll just stick with that for now. And look here. What it's doing is training the model in a given number of epochs. Notice that at every epoch, the loss function actually decreases, and its classification accuracy as to how well the model's predictions actually match the labels we gave our training data increases in each subsequent epoch, to a point that it starts to exceed 95% accuracy, which is pretty good. So we've successfully trained a neural network to learn how to classify this data in just a few lines of code. Think of how easy and concise that was doing it with Keras, compared to how long it was in pure Pythonic code, and how many lines of code it took. Although having done all of this in pure Pythonic code, now you should have a better sense of what goes on under the hood when you specify functions like sigmoid, cross entropy, and so on. And so what this function also does is it returns a history object. It keeps a record of the training loss and accuracy values at every single epoch, which we can get a visual of in matplotlib. So what we'll do is actually set a variable h for history is equal to the return value of our fit function. We'll rerun that. And inside of this cell, I'll just wait for the epochs to finish and fast forward this video. Alright, and with the pyplot subpackage plt, we will make a plot of the accuracy values which we can access from h.history. And from this history attribute, we can access all the values of our accuracy from the key ACC for accuracy. We will give our plot a title, plot.title of accuracy. We'll also label the horizontal x-axis, plt.xLabel. We will label that one epoch. And we will give the plot a legend which takes in a list, but we only have one curve in our plot. Well, we're only going to have one curve in our plot, which we will call accuracy. Let's run our cell. All right, and notice how at around 10 epochs, our model pretty much reaches maximum accuracy. So realistically, we didn't really have to do 500 epochs. Again, it really depends on the type of training data that you're working with. All right, now inside of a new cell, let's actually just copy and paste this code. And instead of plotting the accuracy, we'll plot the loss. We will rename our title and legend as well to loss. Run our cell. And looking at this, it's clear that the loss, the error, is completely minimized once we get to about 10 epochs. And then it just kind of saturates from there. So clearly our network model, after numerous epochs, came up with a really good model in classifying our data with minimal error and maximal accuracy, all in a few lines of code. 5 lines of code to be specific. Now it's time to actually display our model. Let's do that in the next video.